Hi, today we're going to talk about Le Chatelier's principle. So if you took chemistry in high school, you probably learned about Le Chatelier's principle. And basically what you learned was something like this. When a change is introduced into a system, and I should add a system at equilibrium, even though it doesn't explicitly say that in your book, the system will move to counteract the effects of the change on the system. So what is this saying? Let's say you have this reaction of carbon monoxide reacting with 2 hydrogen gas to make methanol. If you add more carbon monoxide, what's going to happen is that the system will get rid of at least part of that extra carbon monoxide by converting it to products. Or, let's look at that same reaction under different conditions. If you add more methanol, the system will get rid of that extra methanol, or at least part of it, by converting some of it to reactant. Now, when I was in high school, they just said the system gets rid of the extra. What does that mean, though? I mean, it's pretty vague. So what I want to do is I want to go through and look at Le Chatelier's principle from an equilibrium perspective. So going back to talk about what we just talked about in terms of calculating equilibrium concentrations and equilibrium constants. So again, we're going to use our generic reaction with the reactants A and B. So we have A moles of A, B moles of B, making 2 products, C and D, C moles of C, and D moles of D. And then our equilibrium constant we learned was products raised to their coefficients over concentrations of reactants raised to their coefficients. So what Le Chatelier's principle is telling us is that when products are added to a system, you're going to have a larger number on the top of that fraction, and you are no longer going to be at equilibrium. Your reaction quotient Q is going to become larger than your equilibrium constant. So to get back to equilibrium, the system is going to have to change somehow. And right now, the reaction quotient is too big, so it's going to reduce the number of products and increase the number of reactants, and then you'll have a slightly smaller number on top divided by a slightly larger number on bottom, and that should get you back there. So another way to think about it is if you have a system at equilibrium and you add reactants to that system, then you're going to have a larger number than you used to in the fraction. And so your reaction quotient, because remember, we're no longer at equilibrium, it's going to be Q rather than K, your reaction quotient is going to get smaller. It has a bigger number on bottom. You're dividing by a larger number than you were before, so it's going to be a smaller number. So how do you change that? You change that by transforming reactants into products, basically making that number on bottom smaller and the number on top larger, and that should get you back to equilibrium. So let's look at an example of this. This reaction is between ethyl acetate and hydroxide, which can combine to form acetate and ethanol. So this reaction was run, and they measured the equilibrium concentrations of all the products at the end, and they got 0.65 molar ethyl acetate, 0.003 molar hydroxide, 0.085 molar acetate, and 1 molar ethanol. And if you plug those into the expression for the equilibrium constant, what you get is K being 435.9. So let's say you take that system at equilibrium and you just throw a whole bunch of acetate in. And so now your acetate concentration is 2 molar instead of 0.85 molar. So let's look at the system from a mathematical point of view and just calculate what the reaction quotient is. And so we plug this into the mass action expression, where we have the 2 products, acetate and ethanol, on top, the concentrations of ethyl acetate and hydroxide on the bottom. And so plug in the numbers from the problem, and what you get is 1026. Now, if you look at this value for the reaction quotient, what you're going to see is that it is much larger than the value for the equilibrium constant, which first of all means that it is no longer at equilibrium. So what's going to happen is either the reverse reaction is going to happen or the forward reaction is going to happen so that the system moves back to equilibrium. Now, how is that going to happen? So the high school version of Le Chatelier's principle says, hey, we've added products. The system is going to shift to reactants. whatever that means. Again, in other words, you're going to make more reactants than you had before. So again, what does that even mean? Let's figure this out mathematically by doing an ice table. So what I've done here is I've filled out the ice table with the concentrations that we know, and then I've added the change with X, and we know from our high school level version of Le Chatelier's principle that we should be making more reactants, so I've put plus X on that side, and we should be therefore losing reactants, so that would be minus X on the other side. And so you get these values at equilibrium, and then you can just plug them into the expression for your equilibrium constant, get this. Now I'm going to spare you the algebra, you can work it if you want, but basically what we come down to is x equals 0.004, rounded. So let's plug that into our ice table, and what we see is that the concentrations do shift towards reactants, but how much do they shift? Not very much. And that's the important part that you need to understand when you say shift towards reactants. What does that mean? It means some of the extra that you added will shift towards reactants. How much depends on things like what's your equilibrium constant and how much extra of the product did you add. So thinking about Le Chatelier's principle from an equilibrium viewpoint gives us a much deeper view than we have with that simple little phrase that we might have learned in high school. So now what I want to do, I want to talk about Le Chatelier's principle applied to things that aren't concentrations. So for example, if you have a mixture of gases at equilibrium and you change the volume of that gas, the concentrations of the components of your gases may also change. Why would that be true? So let's consider the following system, where we have N2O4, and that is in equilibrium with NO2, because NO2 dimerizes, in other words, it reacts with itself to form a new gas, N2O4. So just putting NO2 in a container, you're naturally going to get some N2O4 or vice versa. So we set up the system at 25 Celsius in a 1 liter container, and at equilibrium you can observe the partial pressures of gases, which are listed here. So let's calculate Kp. So here's our, that should be our expression for Kp, except I put concentrations instead of pressures, so please pretend those are pressures. And that's going to be 0.979 squared, the partial pressure of NO2 divided by the partial pressure of N2O4, which is 0.122, and so we calculate that to be 7.86. Now remember, that is our equilibrium constant. Now think about what happens to the pressures if the volume is compressed to 0.5 liters. So remember that pressures and volumes are inversely related, so if our volume is halved, our pressures will double. That means that our partial pressures for both gases are different. So now we have double the amount of N2O4 and double the amount of NO2. What does our reaction quotient look like after we compress the gases then? Well, we can go ahead and plug those in again, pretend that's partial pressure there, and we get a different calculation, and we end up with 15.7 for our reaction quotient. So if you look at that, that is larger than our equilibrium constant, which means we're going to have a trend where it's going to want to go back towards reactants. So one of the ways to understand that is to think about the way that a system can counteract a change in pressure, and that is that it will try and decrease the numbers of moles of gas. So if the pressure increases, it will try and decrease the numbers of moles of gas. And actually, then if the pressure decreases, it will increase the number of moles of gas. So if you think about the ideal gas law and our reaction here, pressure is not the only thing that's linked to volume. The number of moles is also linked to volume. And so what we can do is we can change the pressure, try and get back to those nice equilibrium pressures by decreasing the number of moles overall. So you can see that in this particular equation, we have 2 moles of products, but we only have 1 mole of reactants, and so to decrease the pressure, we're going to decrease the number of moles by shifting towards reactants. And that is what our reaction quotient told us we should do, is to shift towards reactants. Okay, one more thing that is not a concentration or a pressure that can also affect what happens at equilibrium. So let's think about heat and what happens if you add heat to a system. And the easiest way to think about this is to think about a non-chemical equilibrium. This is more of a physical equilibrium where we have liquid water turning into gaseous water. And it does that if you add heat. So now think back to what we talked about when we talked about phase changes and why you need to add heat to a system to turn a liquid into a gas. From Le Chatelier's principle point of view, if we think of heat as a reactant, like one of our reactants is liquid water and the other one is heat, and that will give us a product of gaseous water, then by our high school version, we can just say, okay, here's what happens when we put heat into the system. That's a reactant, and then the system will shift to make more products. So adding heat means more water will evaporate, and that makes a lot of theoretical sense to people. So if you add more reactants, the system will create more products. And if you take away reactants, if you take away heat from the system, in other words, if you cool it, then the system will create more liquid water. So as you cool the system, gaseous water will condense and turn into liquid water. But let's look at that from a molecular point of view. So here's our equilibrium. We have some liquid water molecules that are held together by hydrogen bonds, and then we have some gaseous molecules that are flying free. So if we add heat, that means there's extra energy in the system, and that extra energy has to go somewhere. So where is it going to go? Well, one thing you can do with heat, it's energy, right? And if you put energy into a system, you can break bonds. So what you can do is break the bonds that are holding some water molecules to each other and turn those water molecules into gas. And then you can think about the opposite happening if you're cooling the system, so you're basically removing heat. Where does that energy come from? That energy has got to come from somewhere, and one of the ways you can get energy out of a system is by forming bonds. So remember, forming bonds gives off energy, and that energy can then leave the system to cool the system. So you could do a similar sort of thing to think about exothermic reactions in which heat is a product. We'll talk about that a bit in class. In the meantime, what I want you to take away from this video is that Le Chatelier's principle, as you learned it in high school, if you took chemistry in high school, is really just a simplification of what is going to happen when we do our equilibrium concentrations after something is moved away from equilibrium. And so it is a simplification of a very complex system. I hope this was helpful, and I will see you again soon.